So, sa trial 2 naman, medyo magkakaroon tayo ng ano dito, ng reference in a way na mas papapadali niya. Okay? So, to get delta T1 yung i-adjust natin dito ngayon, no? Kasi yung delta T, pwede natin siya ma-compute based dun sa ating nakuha mga values. Kasi gagawin niya is i-adjust niya based dun sa ating mean area. So, lagyan na lang natin ng apostrophe para ma-specify na ito na yung second trial natin. So, delta T1 is just you take the area 1, so that's area 1, and then divide that to your mean area para ma-adjust niya. And then, syempre, i-multiply mo to ngayon dun sa original mo na delta T, which is yung delta T1. So, ganun lang siya kasimple para ma-adjust. Okay? So, in this case, gawin ko siya muna dito. So, that will be equal to a sub 1, that's 66.2376, and then the mean area is 54.1354, and then we multiply this with the original. So, just to give you an idea of how this movement or adjustment works, so, i-adjust nitong ating new temperature in a way na ilalapit niya dun sa designated niya na area. Bakit? Kasi itong differences na to, usually, hindi na siya gaanon malaking effect dun sa ating material balance. It's just that dito lang sa ating temperature in computation with the area. So, kapag need niya pa na i-increase yung kanyang temperature, mapapansin nyo, mas mababa yung mean na nakukuha compared dun sa area niya. So, in this case, kapag mas mataas tong area na na-compute mo sa una, based dun sa mean, tataas pa niya mismo yung kanyang temperature gradient. Now, in this case, since mas mababa to, dito sa ating area, ditong dalawang to, so ang mangyayari dyan, i-decrease nila ngayon yung temperature gradient para ibigay yon doon sa ating delta T1 na mas kailangan na mas malaking temperature gradient. Okay? So, I'll just be doing the same thing for this process. So, yun lang. You can also do that to check your answer. So, there will be delta T2. So, you get the area 2 for this case. So, 45.2245, then divide it with the mean, so 54.1354, and then multiply that with your original delta T1, that's 14.01. So, you'll be able to get 11.7040. So, mapapansin nyo, yun nga, na-decrease na siya compared dun sa before na temperature. So, for our 3, we have, actually, most of the time, sa trial 2, nakukuha na yung tamang sagot. Kasi, yung adjustments kasi ng mga values natin dito, hindi na siya ganun kalaki talaga. Kaya, usually, nakukuha na siya. Pero, syempre, sa rare cases, hindi siya ganun kadaling mahanap. Sa mga rare cases lang naman. And hopefully, hindi ito yung rare case na yan. So, we have now delta T1 prime to 3 prime. So, ito na yung mga bago nating temp. And we'll be using this to find naman ulit yung ating mga bagong temperature dito. So, ano ba yung ating magiging boiling point rise ngayon? Ito na yung tanong. Ano ba yung bago natin boiling point rise? So, let's go back to these values. If we would take a look at this L1 and then yun sa ating feed, if we will be making a balance from that, so alam naman natin na L1, so that's 10153.6880, and then times XL1, that is equal to the feed times 0.10. So that's 13608 and then times 0.1. So it will give us the value of X sub L, which is around X sub L1, which is equal to 0.1340. So yung assume natin before na around 15%, medyo mamumove lang siya to a lower value na 0.13. So, gagawin natin, yun na yung ating magiging bagong X sub L, 0.13. Because yun yung ating nakuha dun sa ating value din. Then, to obtain XL sub 2, so, gagawin lang natin ngayon is, sundin natin ulit yung same procedure na yan to find XL sub 2. So, with that, XL sub 2, so, you do the balance in the second effect. So, that would be equal to 6.526.8567, and then times X, yung pumapasok, and then L3, pwede kasi sa L3 lalabas, so we have 2721.6 times 0.5. So you'll be able to get a value of 0.2085. Okay, so ito yung ating fraction na bago, and before, we assumed na yung ating value is 0.15 and then 0.23. So with that, doon natin ngayon i-check yung ating mga fraction, knowing na meron na tayong this kind of mole fraction. And by the way, since meron na rin tayong delta T1, so we don't have to like isipin pa kung ano ba yung ating magiging boiling point rise. Kasi basically, if meron na tayo nito, makompute natin yung TL1, TL2, and then the rest. Okay. So from this, let's find TL1. So same procedure lang yung gagawin ko dito. Di na ako dalubhasa sa pagsusulat ng mga formula. Same lang din yan. Okay, so from this, makikita natin na we have 376.7679 and that's 218. Yun na yung leak or temp. Knowing na ang ating fraction is 0.13, so we go back to Paris Handbook. Medyo magulo na. Burahin natin. So we have 218.5. So that's around 220. And then you go to sodium chloride. And then you intersect that. And then you move to 0.13. So that's around here. Okay. So, yon. Okay, so, mapansin nyo, nilapit ko na sa 4 kasi, 4, 13 lang naman siya sa 0.13. So, it's around here. So, yun nga, kung mapansin nyo, yung atin sa dapat na tamang BPR is 4 degrees Fahrenheit. So, yun lang naman yun. So, BPR from the figure should be BPR 1 prime is equal to 4 degrees Fahrenheit, so divided by 1.8 Kelvin. So that should be our TV1, our BPR. Then we'll be able to get TV1 from that. So we have to like 376.7679 minus 4 over 1.8. So yun ang ating TV1. So we have 374.54567 Kelvin. Okay, and then we proceed with TL sub 2. So we have 374.5457 and then minus delta T2, so we have 11.704 T. So we have 362.8417 Kelvin, and then knowing na meron tayong BPR sub 2 prime, we take that on the figure again. So we know naman na itong TL sub 2 is yung liquor solution temperature. Let's convert that to Fahrenheit. That is equal to 193.4451 degrees Fahrenheit. So with this, with 193, so we have 190 around here. So that's 193, and then we intersect to sodium chloride, and then we have there around I think that's 0.20, 0.21. So we have 0.21 around here. Okay, so that's around that value. Okay, so as you can see, the boiling point rise is just about I think that's 8 point something, if I'm not mistaken. So as you can see, the boiling point rise is just around 8.1, I guess, or 8.2, because this one's 8.5. So let's just use 8.2. In that case, our boiling point rise should be 8.2 instead of 10. That's what our assumption was. So we have 1.8 Kelvin, and then we will be able to get TV2 from this boiling point rise 2. So we just have to subtract that from our value. So our TV2, we have 358.2861, and then finally we have our actually we're done. Okay, so we're done with all the necessary temperatures, and then we need to find now our enthalpies at this case. So with this, let's just copy this and then paste it here so that I don't have to write it again. Okay, so find all the enthalpies. So that's our next step. So for our HV1, so syempre mababago tong mga values na to. Kung mapansin nyo, yung TV1 is 374 ngayon. Before, it's 378. So, 375. So, mapapansin nyo, hindi naman siya sobrang laki. For example, ito, 356. For TV2 is 358. So, actually, hindi siya sobrang laki ng difference. Kaya, sabi ko nga, after second trial, usually, tapos na yung ating solution. Nakukuha natin yung tamang sagot. Pero, let's just continue. So, you will be using this to find all the enthalpies. So, fast forward ko na lang ulit to. So now that we have already found all the enthalpies, so let's find the CPL sub 1 again. and then the CPF. So it will be retained, but for the CPL1, let's adjust them. I'll be using x sub 1 is equal to 0.13 for xl sub 1, and then 0.20 na lang siguro dito para ma-minimize yung ating mga decimal points dito sa area na to kasi medyo hindi nagkakasya. Either way, you can just use 0.21, but the effect naman nun will be very minimal kasi kung mapapansin nyo dun sa equation natin, it's 1.95. The big factor is 4.18, pero you could just use 0.21 just to counter check. I'll be using 0.20 instead. Okay, so for those things, kung medyo hindi naman ganun kalaki yung effects, you specify that in your computation. For example, ginamit niyo is 0.21 instead kasi rounded nga, pero ako 0.20 na lang para mas maliliit yung values dito. I mean, yung decimal points kasi hindi nagkakasya lang dito for this sake ng computation. No? Pero syempre, mas better kung 0.2085 na yung gagamitin niyo dyan. Anyway, so I have CPL1. Okay, and then I'll be fast forwarding this video again. Okay. Okay, so now that we already have these two equations to unknowns, let's find the values of L sub 1 and L sub 2 and the rest of the unknowns. Okay, so L1 is 10,154.0880, that's kilogram per hour. And for our L sub 2, we have 6,500.8557 kilograms per hour. And then for our V sub 1, we know that that's just obtained from our balance. So we have 13,608 and then minus 10,154.0880. So we have 3,453.9120, that's kilograms per hour. And V2 can be obtained from the rest of these values. Now all of these values, we can now check for the heat per effect. So we have Q sub 1 is equal to, you just use the same equation as here. So I'll just be using this one to evaluate for Q1. That's kilowatts. So we have 3,151.3280 kilowatts. And then for Q2, we have 2,161.381 kilowatts. And then for Q3, we have 2,328.9360 kilowatts. Now, the next would be the area. So you just employ the same concept, and you will be using the new area, not the original. So we have this area 1 apostrophe. So you'll be using that 9.3, 11.7, and 19.7 respectively. So you'll be able to obtain a value of. Okay, so for this, the mean area would be equal to 3369. And if you would be taking the relative percentage difference of each of them, so the highest will be coming from the third area, and you will be able to get around 2.79% relative difference. So that's just below 5%. So we can now say that this is the correct assumption, or let's just say this is the area itself. Okay, so when reporting the answer, you'll be using this a sub m instead. Okay, so that's our area. So we could say that from this problem, the area, the surface area for each effect is around 53.3 meters squared. Okay, and the next question would be determine the steam consumption. So steam consumption is quite easy to determine. If we have Q1, we know that this is also equal to S1, S and then lambda S. So if we have Q1, this is equal to S, and then we have this lambda S. So knowing our lambda S, we already obtained that value. And actually, that's not lambda S, but HS minus small h. So this is equal to S, and then times this one, 2249.7. So we multiply with this, and then we're left with our value of S, which is equal to, so we have S equals 5043.7540 kilograms per hour. And don't forget to convert your kilowatts in terms of kilowatts per hour, kilojoule per hour first, because you won't be able to get this unit. So now let's move on with the steam economy. So we know very well that the steam economy is the vapor over the steam, and if it's multiple effect, then you should be adding all of the vapor, and then you'll be able to obtain the total vapor. So that's just how simple it is. So what we have is this total vapor, and this total vapor was actually obtained before. This is equal to 10886.4 kilograms per hour. So we can say that this is equal to 10886.4, and then if we divide this by S, so let's just add something like this. Okay, so now that we have V over S, so this is equal to 2.1584. So 2.1584. So our steam economy is equal to 2.1584. Now, you might be thinking, why is this greater than 1? Now, for multiple effect evaporators, it's always common to be getting values that are greater than 1. The one that I was actually talking about that should be hypothetical and should not be existing is the one in single effect, because single effect, technically you won't be able to get a vapor that would be greater than the amount of steam. But for cases like this, because we already know that this steam is fed at just at the first effect, wherein all the vapor is coming out actually at the 3 effects that we have. So you just have to add those vapor released from each effect, and then by just the virtue of knowing that each effect is releasing the vapor, you would know that it's actually would be greater than 1 for the steam economy, because steam is just fed at the first effect, and the vapor is kept released in the succeeding vapor chest or succeeding effects. So that would practically be greater than 1. Okay, and the reason why this multiple effect is always a better choice in economy is that for steam consumption, which are very expensive, so I'm talking about these steam that are used in the large scale industries. So instead of doing a single effect, they would be using this multiple effect, because the cost of the steam is really that high. So they'll be buying something like, or producing this heat generation system. So constructing that heat generation system would really employ a lot of money. So instead of just using batch process for the evaporation and then just using one single evaporator, they'll be employing a lot of evaporators so that their steam would be maximized and will be efficient in they will be employing these multiple effects so that their steam would be maximized. They will be able to maximize the use of this steam. And usually these evaporators in single effect, they're mostly employed in cases when they're just small scale process and you don't need much steam. It's like the steam is like not really expensive, so you can just use it and then just condense it and then you throw it. That's all. And or maybe you just use it for your wastewater treatment. But the thing is, those companies are really not really large if they're using such kind of method. Okay, so I think that's all for evaporation. I hope you've learned something. I'm sorry for skipping this very long computation because it really take a lot from me. I don't know if how long will this video take, but sana hindi siya umabot ng sobrang tagal kasi talagang mahaba siya. And just to mention yung ating balance dito, we've employed a lot of algebra dito, kaya medyo matrabaho siya. But anyway, nakuha naman natin yung tamang sagot. So, ayun lang. Just to remind you, kapag gusto nyo pa itong i-further, i-trial pa ulit, I'm sure makukuha nyo din is 53 point something na. You just employ the same concept right here and then you'll be able to find the exact delta t. So, probably magkakaroon na kayo ng exact ding fraction. But dun sa ating graph naman, kung mapapansin nyo, medyo sakto na yung mga fraction natin. Okay? And kung mapansin nyo, yung ating unang assumption is very malayo dito, 66 and 45, no? Pero after the second, na siya, pare-parehas na siya almost. Kaya, yun nga, kahit medyo malayo yung assumption nyo, basta second trial, medyo maglalapit-lapit na yung values niyan. Okay? So, yun lang, and let's move forward na sa crystallization. Okay? Thank you.